The very last type of trait that we're going to talk about is what you see here, polygenic inheritance. The unique thing about polygenic inheritance is that it's not an either-or situation. Instead, as you look at the graph that you see in the bottom left-hand corner, there is a spectrum of traits. Even though we're talking about one trait, the possibilities go, in this case, from one extreme to the other. There are many examples that we can talk about in terms of polygenic traits, but the fact of the matter is that when we look at each other, most of what we see about each other happen to be polygenic. Eye color, hair color, height, weight, and in the case that we're going to talk about here, skin color. What makes polygenic traits polygenic is embedded in the name, poly. Poly, of course, is a prefix that means many. So polygenic means many genes. In every circumstance that we've talked about up to this point, for any trait, we've always talked about inheriting one gene from the mother and one gene from the father, and the child or offspring has a pair, and depending on the type of trait, those pair operate in a certain way. Maybe it's complete dominance, maybe it's incomplete dominance, and there's a blending and so on, but there was always just one gene from mom and one gene from dad. That is not the case when it comes to polygenic inheritance. Instead, and using skin color as our example, there are 6 genes that are inherited for that one trait of skin color. So obviously then, with 6 total genes, there are 3 that you inherit from your mother and 3 that you inherit from your father, and that gives you the total of 6. The result is a blending. And so with blending, I hope what comes to mind is the idea of incomplete dominance, because these are, in addition to being polygenic, incomplete. If we look at the example that we have here, and we look here where we have parent number 1, you can see 6 circles, and those 6 circles are there to represent the 6 genes that that parent has for the trait of skin color. You'll notice that some of those circles are colored in. Our skin color is the result of the formation in our body's skin cells of a substance called melanin. So if I have a circle that in this case is colored in, we're going to say that that represents a gene for the production of melanin or skin pigment. And if there's a circle here that lacks color, then we're going to say that that's the gene that does not produce melanin. And so with this parent number 1, we've got 6 genes, and you of course can see that 3 of them are colored in and 3 of them are not, meaning that this person's skin color would be very middle of the road. If we looked over here at our graph, they would be somewhere here in the center. Not real dark, not real light in their skin pigmentation, but somewhere in between. Parent number 2, same situation. They have 3 that are colored in, 3 that are not. And so they too would fall very much in the center of our bell curve-like graph that you see in the lower left-hand corner. But let's think about what would happen if those 2 parents had a child. If parent number 1 has 6 genes, they get to pass on half. They get to pass on 3. And the same thing would be true of parent number 2. So think about the possibility. Let's say that parent number 1 passes on this one, and this one. And parent number 2 passes on this one, and this one. That child inheriting 6 genes, 3 from each parent, that all did not code for the production of melanin, they would be very much on this end of the spectrum. They would have very light skin pigmentation. At the same time, those 2 parents could produce something very different. Let's say that parent number 1 of its 6 genes donated this one, and this one, and parent number 2, this one, and this one. That child would be born with 6 genes that all coded for the production of melanin or skin pigmentation, and so they would fall very much at this end. So same two parents, and yet very different results. Now, there's just as likely a chance, or actually a greater likelihood, that a child of these two parents would fall somewhere in between, but there are the possibilities of both extremes. Think about this in terms of your own family, maybe in reference to height. How many of you, say, are taller than your tallest parent, or perhaps shorter than your shortest parent? Just like the children that I've described here were either darker than their parents or lighter than their parents. The same could be said for height. The same could be said for eye color. All of those polygenic traits, there are so many varieties and combinations that there is a lot of uniqueness. We are not going to do a Punnett square for this trait, and just by looking at this, I hope you can see why. We're looking at just crossing one trait here, and because of the 6 genes for that one trait in each parent, you end up with a Punnett square that would have a potential for 64 blocks. Please just understand the basic idea of polygenic traits, that it is multiple genes being passed down by each parent that all contribute to one trait.